that you had for today. So the first question there was, petrol is obtained from crude oil in an oil refinery. Name the process. So naming the process there, fractional distillation. Petrol is obtained from light gasoline. Now we, excuse me, we call that the petrol fraction. Like Americans use the word gasoline, we call it petrol, but they wanted another fraction that we can obtain from petrol from. So naphtha is our answer there. So naphtha. Your definition of octane number, well, octane number is the tendency of fuel to resist knocking, and remember that it's based on a scale where 2 to 4 trimethylpentane is assigned a value of 100 and heptane a value of 0. Then they asked you for the name, that's your 2 to 4 trimethylpentane, and you should be able to draw the structure. 2 structural features of hydrocarbons that give them high octane numbers, well, short, chained, highly branched, or maybe contain cyclic structure. Now, I'm going to go to the show me board now to do the calculation there, but just let's do the theory there first before I move on. Why was a polystyrene cup used instead of a glass beaker? Well, because polystyrene is a good insulator, so any heat that's going to be made in the cup through the reaction of the acid and the base stays within the cup. It's not lost to the surroundings, okay? And then 3 precautions that should have been taken. So there are the precautions, like I suppose the big one really is using a sensitive thermometer that will measure to within 0.1 of a degree, adding quickly, adding the base to the acid quickly stirring it, so that the heat is being distributed throughout the solution, applying a lid, all of those scenarios that we went through yesterday when we were in the video would be perfect for that. Now, just going to go to the show me board now to do the calculation. Okay, so look, what information do we need to take? 100 cubic centimeters of a 1 molar, it's a monobasic acid, so that's important to note that. The rising temperature was 6.5 degrees. They gave you the specific heat capacity, and they told you that you have 100 cubic centimeters of each, okay? So, first step that we're going to do is calculate the number of moles of HCl, okay? So it's a solution, V by M all over 1,000. So 100 cubic centimeters, it was a 1 molar acid divided by 1,000. So that's 0.1 moles. So that's step 1. Step 2, then you're going to calculate the heat that's generated in the cup using your formula MC theta. Now, M is mass in kgs, right? So we have to get the mass of the solution now first before we can do any more. They told us that you had 100 cubic centimeters of acid and 100 cubic centimeters of base. So the total volume is 200 cubic centimeters. They told you to assume that the density was the same as the density of water, 1. So to get the mass, you're going to multiply 1, which is the density, by the volume, which is 200. So you're getting 200 grams. But you must convert that to kgs by dividing by 1,000. They told you to use 4.2 for the specific heat capacity, and the rise in temperature was 6.5. And then when you calculate the heat that's made in the cup, you're getting that in kilojoules because your specific heat capacity value was kilojoules, so stick with kilojoules. Now the third step then, of course, is that you're equating moles of acid, okay, to the heat that you made. And then your definition for heat of neutralization is the heat change that occurs when 1 mole of H plus ions. So divide both sides there by 0.1 to get 1 mole. So 1 mole of HCl, then when you do that, minus kilojoules. It's all in kilojoules now per mole. And remember that 1 mole of HCl donates 1 mole of H plus ions. So you can say minus 54.6 is your answer, kilojoules per mole, put in the units. Lads, if it was sulfuric acid, 1 mole of sulfuric acid will actually give us 2 moles of H plus ions. Okay, all right, so be careful with that. Like when you have your answer here for 1 mole, that's equivalent to 2 moles of H plus ions. So you would have to divide your delta H value by 2 if it was sulfuric acid. Okay, now I want to go back there now to the photos. That was that one. The next question that you had there then, next question that you had there then was this one. So this one was production of ethene. Now you should be fine. At the marking scheme, these are pre-questions. I'm going to post the marking scheme as well, but it's a little bit mixed up for some reason, so just follow through. But anyway, drawing the label diagram should be fine. It's in your revision book on page 193. You'd have to show boiling tube clamped horizontally. You've got the ethanol soaked in glass wool at the end of the boiling tube. Remember, the purpose of the glass wool is to hold the ethanol in place. The aluminium oxide, white aluminium oxide in the middle. You're heating the catalyst, the aluminium oxide. So draw a Bunsen and label a Bunsen. There's no point in drawing a Bunsen if you don't label it. You're not going to get any marks for it, okay? The next thing that you'll do then is you'll draw your tubing and again label the delivery tubing. You need to label everything, and then you're labeling your test tube of water in the trough of water, and you're collecting the ethine by downward displacement of water, okay? And remember, ethine is not polar, so it's not soluble in water. That's why you can collect it like that. Now, writing a balanced, writing a balanced chemical equation. Well, how do you production of ethene? That's the only elimination reaction on your course. So it's ethanol going to ethene, and you're showing the water as well. And don't forget to write the aluminium oxide above there, okay? Why are the first few tubes of ethene discarded? So remember that the first few tubes are a mixture of ethene and air. So we discard those because we want to get all of the air out of the apparatus first before we start collecting pure test tubes of ethene. What precaution heating stopped? Remember now, if you turn off that Bunsen, the way the apparatus is drawn, what's going to happen is that the contents of the test tube will get cold. Cold air contracts, and you will suck cold water from the trough into a hot boiling tube till crack. So before you turn off the Bunsen, you have to take the tubing, raise the whole apparatus above the level of the water, so the tubing's above the water, so that when you do turn off the Bunsen and stop heating, you're just sucking back air, you're not sucking back water, okay? And describing the test now. How could you show that ethene is unsaturated? Well, you're going to use your bromine water or your acidified KMNO4. Remember that you say stopper and shake and the colour change, okay? Now, I just want to do the calculation here. So remember now that ethanol production of ethene, it's a 1:1 ratio, so 1:1. So now you were told here that they used 2.4 cubic centimetres of ethanol. That's the volume because it's cubic centimetres. And they're also telling you that the density of ethanol is 0.8 grams per cubic centimetre. So the first thing you're going to have to do there now is you'll have to get the mass. Because remember your steps. Step 1, all the time, number of moles. And we need mass of ethanol to divide by the MR to get the number of moles. Ethanol is a liquid, so you will most likely be given ethanol in cubic centimetres in volume. So you must be able to do that. My dear Vera, cover over mass, so your formula for mass is going to become density times volume. The density they told you was 0.8, the volume is 2.4, so when you calculate that, you're getting 1.92 grams. Divided by 46, show the working out of the relative molecular mass of ethanol, and your number of moles then works out to be 0.42 moles, okay? Look at your ratio now, 0.42 moles. You're going to make 0.42 moles of ethene. So step 1, number of moles. Step 2, ratio. So you're going to make 0.042 moles of ethene. Now lads, that's your theoretical yield. According to the balanced equation, that's how much ethene you should make, okay? So 0.04 moles is 100% yield, or your theoretical yield. Now you've been asked to calculate the maximum number of 65 cubic centimetre test tubes of ethene that you could collect. Now, they're also telling you that the actual yield is 60%. Now, you've got a choice here. You can get 60% of the number of moles if you like to get the actual yield, or you can convert moles to cubic centimetres if you want to, which is the way I'm going to do it, and then you can get your actual yield. It doesn't matter. Now, I should have told you actually, they were using 24 litres as molar volume. But look, if you use 22.4, that's fine. I'm going to change to cubic centimetres. The reason I'm changing to cubic centimetres is because my test tubes are in cubic centimetres. So I need to divide the like units, okay? Now, when I multiply that, I am getting, what do I get again? 0.008 cubic centimetres. Now, that is 100% yield. That's your theoretical yield. Actually only getting 60%. So divide by 100, multiply by 60. So your actual yield there is coming out at 605 cubic centimetres. So that's what you're actually making. That's the amount of gas you actually make. Remember that your theoretical yield is always going to be greater than what you'll actually collect. Divide by 65 then, because one test tube has a volume of 65 cubic centimetres, and round off then. You because it's whole numbers of test tubes. So 9 test tubes is your answer. So like I said, now if you use 22.4 or 22,400 cubic centimeters as molar volume, that's fine. But that year, as I said, they asked you to use